All right, some new stuff here, estimating a population mean. The last little bit we've been estimating population proportions or some kind of percentage from a population. Now we're going to estimate the mean of a population. Three things here. First of all, you should know that the sample mean, from what we talked about before, is the best point estimate of the population mean. X bar is the best estimate we can get of mu. Remember, that's true with means, with proportions, and with variances. We're going to learn how to use sample data to construct a confidence interval like we have been doing with proportions for the value of the population mean, and we should know how to interpret it, which we should already know. And number three, we're also going to develop the ability to figure out what kind of sample size we need to estimate the population mean. We're actually going to do that tomorrow, on the next video instead of this one. Requirements. One of these two things must be true in order to do this process. First of all, the population must be normally distributed, or the sample size is greater than 30. That's a CLT. Remember central limit theorem, sample size is greater than 30. Also means we can use normal. All right, margin of error for the population mean, for the margin of error estimate, when you don't know the population standard deviation, which is most of the time. A little bit different here today. Margin of error is the first thing, instead of z-crit, it's t-crit. The critical value is t. We're using a t distribution instead of a z distribution or z-score. And little s means standard deviation of the sample, and n, of course, is sample size. Also today we have to use what's called degrees of freedom, which is brand new for us. And today the degrees of freedom are going to be n-1. df stands for degrees of freedom. We'll talk about more what that means on the next slide. Okay, a bunch of stuff on this slide, a whole lot. If a population has a normal distribution, then a distribution of this t distribution right here, which is x bar minus mu over s over square root of n, is called a student t distribution for all sample sizes of n. Now, that's the distribution we must use to find population means. It was discovered by a guy, believe it or not, who worked at a brewery, the Guinness Brewery, way back in the early 1900s. His name was William Gossett, and he actually did this with samples of beer, to be honest with you. So degrees of freedom, let's see here, degrees of freedom. The number of degrees of freedom, I'm just reading this to you, number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data values. That sounds kind of weird. Okay, best example I can give you right here. Example, if 10 test scores have the restriction that their mean is 80, then their sum must be 800, because 80 times 10 is 800. And we can freely assign values. You can assign the values to the first 9 scores any way we want to, but the 10th score would be determined by what the first 9 scores are. So in this case, we have 9 degrees of freedom, because we have the freedom to choose the first 9 scores, but the 10th score has to be something that will give us 800 when we add them up. So whether you understand that very well or not, for this section, our degrees of freedom are going to be n-1. So every time you see degrees of freedom, and you're going to see that on your calculator, on StatCrunch, everywhere you look, it's going to be degrees of freedom. We're using n-1, which is sample size minus 1. Definition, this is what we just did. This is more degrees of freedom. Actually says pretty much, this first thing says exactly the same thing. We're going to abbreviate it DF. It's n-1 today, and tomorrow in class, n-1 for degrees of freedom. All right, notation. There's the letters. You should know all these. Mu is population mean, x bar sample mean, little s, sample standard deviation, n is how many values there are in the sample, big E is margin of error, and we're going to use t-crit instead of z-crit when we're doing mean. We're looking for population means. All right, important properties of this t distribution. These are important. The student t distribution, it's also called student t distribution, not just t. I'm going to say t distribution all the time, but the official name is actually student t distribution. Is different for different sample sizes, so the curve is different. And I'm going to show the next slide. I'm going to show you what it looks like when sample size is 3 or sample size is 12. The student t distribution has the same general symmetric bell shape as a standard normal curve, but it does have greater variability with wider distribution. So because their sample sizes are smaller, it's going to vary a little bit more, and you should expect that. Number 3, the student t distribution has a mean of 0. T is 0, just like the normal distribution has z is 0. Here's what's different, though. The standard deviation, because the spread is a little bit different, of the student t distribution varies with the sample size, hence the degrees of freedom, and is greater than 1. The normal distribution has, remember, standard deviation equals 1. As the sample size gets larger, the t-distribution gets closer to normal. So the larger your sample size, the better off you are, and the closer to normal it becomes. Okay, here's a picture of the t-distribution. The first of all, this blue, the dark curve you see, that's the normal distribution. Okay, that's what you've been seeing, pretty much since our school year started. The red one is the t-distribution for n is 12, and the orange one is the t-distribution for n is 3. So you can see as the sample size gets bigger, like this is sample size 12, that's sample size 3, the red is closer to the dark normal distribution than the 3 is. So the bigger your sample size, the closer to a normal distribution you get. But we are using t-scores instead of z-scores today. Okay, one example, and we'll close out this video. I want you to see one all the way worked out. It says, listed below are speeds measured from southbound traffic on I-280 near that town in California, which shows up on my cell phone all the time. The SRS was obtained at 3:30 p.m. on a weekday. The speed limit for this road is 65 miles per hour. Use the sample data to construct a 95% confidence interval for the mean speed of the total population actually that travels the road. So what I did first is I punched all these in my calculator in L1. All right, just like we always have. After you do that, I went to one var stats and got some info. I got my X bar, which I need, and I found out it was 60.67. I got my little S because I need the sample. Remember, for our formula, I do need the sample standard deviation. It was 4.075. Now I can find my margin of error, which I need my E. So for my E, I need my t-crit. So I went to inverse norm. Well, on your calculator, it's going to say, if you go to second bars, it says inverse t. It's number 4 when you go to second bars. It says inverse t. And I did the 0.025, blah, blah, blah. You have to punch in degrees of freedom there. My degrees of freedom on this problem are 11 because my sample size was 12. I had 12 speeds down there. So I punched in my t-crit, which is this, times my little s, standard deviation of the sample, over square root of 12 because that's the sample size. When I worked that out, I got 2.59 on my calculator. So that's important. Now to get my confidence interval, I'm going to take this margin of error just like we have been doing with the proportions, and I'm going to add and subtract that from my, I was doing p hat because it's a proportion. Now I'm going to do my x bar. So the way you do your confidence intervals, you do x bar plus or minus your margin of error. So my x bar here is sorry about that. It's 60.67. So I'm going to do that plus or minus my margin of error, which is 2.59. So on my calculator, if I punch in 60.67 minus 2.59, I get 58.08. And if I do 60.67 plus 2.59, I get 63.26. So what can we conclude then? What I conclude is we are 95% confident that the mean speed sorry about that, is within the limits of 58.08 miles per hour and 63.26 miles per hour, which means below the speed limit. Speed limit was 65, so most of the traffic, we're 95% confident that the mean speed, the average speed, is between 58 and 63, so people are doing pretty good. All right, that's all you need. We'll work on some of these tomorrow. Same type stuff we were doing, but just means instead of proportion. You got to keep straight which one you're doing when. Are we doing a mean? Or are we doing proportion? See you tomorrow.